Let's get started on today's notes over solving absolute value inequalities. So rather than having an equal sign in our problem, we are going to have an inequality symbol. So when we review absolute value equations, which we did yesterday, in our most basic example, the absolute value of x equals 4, what are the possible solutions of our variable? What could x be? X could be 4, or x could be negative 4, because the absolute value of either of those numbers is positive 4. So we had two solutions. So solutions to absolute value inequalities are much the same. Our solution is not going to be a simple inequality. It will result in a compound inequality. So as a little review, those compound inequalities are when we use the words or and. And that looks really bad, but that says solutions to absolute value inequalities result in compound inequalities. So what kinds of solutions, or what do your problems look like when your solution is an or, okay? Your problem will have a greater than symbol in it. And I'm going to write this, a greater than. And this will be really good to reference as you work through your problems today. So when you think about this, when you really think about the absolute value of x is greater than 5, what are all the possible numbers that I could plug in for x that would have an absolute value that's greater than 5? Could I plug in the number 2? Is the absolute value of 2 greater than 5? No. What about 6? Could I plug in 6? Is the absolute value of 6 greater than 5? It sure is. Okay. What about, so really any number that's greater than 5 will have an absolute value that is greater than 5. What are the other numbers that you could plug in to x that would also have an absolute value that's greater than 5? Any negative numbers? What about negative 5? No, negative 5, that's not greater than 5, but what about negative 6? What's the absolute value of negative 6? It's positive 6. Is positive 6 greater than 5? It sure is. So actually, any of those numbers that are negative, negative 6, negative 7, negative 8, negative 9, all of those numbers, if I take the absolute value of those, I'll also get a number that is greater than 5. So that's why when you see a greater than symbol in your problem, your answer will result in an or compound inequality. My answer is this or that. Okay? Now, when we get to the examples where we have an and in our solution, you'll see a less than symbol. So in this problem right here, the absolute value of x is less than 5. Well, now, our numbers cannot be greater than 5 that we plug in for our variable. They have to be less than 5. Okay? So what are the values that I could plug in to this inequality, and I would get the absolute value of that number is less than 5. What about 3? What's the absolute value of 3? It's 3. 3 is less than 5. Okay, that works. What about 0? 0 also works. The absolute value of 0 is 0, so that's less than 5. What about negative 2? Negative 2 would work. The absolute value of negative 2 is positive 2, and positive 2 is less than 5. What about negative 4? That would work. Absolute value of negative 4 is less than, or is 4, and 4 is less than 5. So really, all of these numbers, but if I plug in the absolute value of 6, that's 6. So this right here, that's too many. 6 is not less than 5, it's greater than 5. So really, any of these numbers in between negative 5 and positive 5 are in my solution set. That's an and inequality. Okay, your solution has to be less than 5 and greater than negative 5. So let's move on to some of our examples, and you'll probably want to refer to these notes up here as you go through your problems today, especially because this is a really difficult concept to just understand. So a lot of students really just want to memorize the process, and maybe hopefully the more examples you do, the more problems you do, the better understanding will come. So the steps to solve an absolute value inequality, just like when you solve an equation, you're going to want to isolate the absolute value expression. And you do that using the same process that we used yesterday, and you'll set up two cases just like we did with equations, except this is going to deal with inequalities. Now, what do your cases look like? Yesterday, you had to, or with equations, you just basically one side of the equal sign, you changed every term to a negative, right? You didn't change every term to a negative. You multiplied every term by -1. Okay, so if you have one number on one side of the equal sign, you just made it negative. So in today, what you're going to do is, in one case, you are going to drop the absolute value bars and just solve for the variable. So you just solve it like it is a regular inequality. In your next case, you're going to drop the absolute value bars, but you're going to flip the direction of the inequality symbol and then multiply the entire expression on one side by -1. So you switch the sign of the number. That's basically what that means. We're going to switch the sign of the number. So let's get into these two cases. We have an OR example and an AND example, and they look exactly the same except for our inequality symbol. So I'll show you why our solutions look different. So when we solve this one over here, the absolute value of 2x plus 5 is greater than or equal to 9. We're going to set up our two cases. Now, I know that this is an OR case, and I'm just going to write that up here because that will really help you today. This is going to be an OR solution, and I know that because it's got a greater than or equal to symbol. So the first case, when I solve it, it's going to look like this. 2x plus 5 is greater than or equal to 9. Then I set up the second case, and it looks like this. 2x plus 5 is less than or equal to -9. So I switch the direction of the inequality symbol, and I switch the sign of the number. Okay, so now, and then we just solve. So if I'm solving for the value of x, in this case 1, I'm going to subtract both sides by 5. And I'm left with 2x is greater than or equal to 4. And then I'm going to divide both sides by 2, and I get x is greater than or equal to 2. So that's one part of my solution for this problem. In case 2, 2x plus 5 is less than or equal to -9. I'm going to subtract 5 from both sides, and I get 2x is less than or equal to -14. When I divide both sides by 2, I get x is less than or equal to -7. So you can absolutely write your answer just like this. X is greater than or equal to 2, or x is less than or equal to -7. And then how would I graph that? If it's greater than or equal to 2, close dot at 2, that's greater than. Less than or equal to -7, close dot at -7, that's my solution. How would I write this in interval notation? -infinity to -7, or, I'm sorry, should that be parentheses? No, that should be a bracket. There is a closed dot there. -infinity to -7, or 2 to infinity. Let's move on to the next example. The absolute value of 2x plus 5 is less than or equal to 9. This is going to be an AND example. This really helps me whenever I'm solving problems, because at the end, whenever you solve for your solutions, does it make sense? This is supposed to be an AND example. This is supposed to be an OR example or problem. And, does this solution work? So the first thing you're going to want to do is just drop the absolute value bars and solve it as is. So 2x plus 5 is less than or equal to 9. In your second case, you're going to drop the absolute value bars, 2x plus 5, switch the direction of the inequality symbol, and then change that sign. Okay, so here's what we've got. Let's solve case 1. I'm going to subtract 5 from both sides, and I get 2x is less than or equal to 4. And when I divide both sides by 2, I get x is less than or equal to 2. When I solve case 2, I'm going to subtract 5 from both sides. I get 2x is greater than or equal to -14. When I divide both sides by 2, I get x is greater than or equal to -7. So my solution is x is less than or equal to 2, and x is greater than or equal to -7. You can absolutely write it that way. Let's change colors here. You can also write it this way. X, if it's, and actually I'm going to graph it first and then I'm going to show you how to write it these other ways, okay? So if X can be greater than or equal to -7, close dot at -7, but it also has to, and it needs to be less than or equal to 2, close dot at 2. X can be anything in between. So how can I write that? Well, using interval notation, which is my personal fave, -7 to +2 using brackets. You can also write it like this. X is between, it's less than or equal to 2, and I kind of read it from right to left. X is greater than or equal to -7. You can write it this way, you can write it this way, or you can write it in interval notation. They all mean the same thing. So write your answer however you like it, however your teacher prefers, whatever you need to do. But they all mean the same thing. Let's move on to our additional examples. In example number 1, I have a less than problem. The absolute value of 4x minus 2 is less than 14. If you refer to your notes, that is going to be an and problem. So I'm going to write that word up here just because it helps students a lot. And it's going to be an and inequality, an and compound inequality. So now I'm going to set up my two cases. And the first case, I just drop my absolute value bars. 4x minus 2 is less than 14, and then I'm going to solve. My other solution is I'm going to drop the absolute value bars, 4x minus 2, but then what do? I flip the sign, switch the number. And now I'm just going to solve these two inequalities. So let's solve for the variable in this first inequality. If I add 2 to both sides, I get 4x is less than 16. And now if I divide both sides by 4, I get x is less than 4. There's one solution. Here's my other solution. 4x minus 2 is greater than -14. If I add 2 to both sides, I get 4x is greater than -12. If I divide both sides by 4, I get x is greater than -3. So now if we graph this, x is greater than -3, that's right here. Greater than is going to be that way. And x is less than 4. Less than is going to be that way. So now we're just going to connect them. This is what my solution looks like graphed. How else can we write this? I'll change colors again, if it'll let me. Let's do this color, just because. So now how can I write that? Well, x is less than 4 and greater than -3. I read it backwards. So that's how I can write it. A lot of students in Algebra 1 write it this way. You can also write it in interval notation, which is what I prefer, from -3 to 4. And I use parentheses because we have open dots. We're not including those endpoints. So let's move on to our second example, number 2. So number 2 is the first type of example where we don't have our absolute value expression isolated on one side of the equal sign. So that's actually the first thing that I need to do in this problem. So I'm going to subtract 5 from both sides, because I get rid of that part first. And this is 2 times 3x minus 9 is greater than or equal to 23 minus 5 is 18. And now I'm going to divide both sides by 2. When I divide both sides by 2, I get the absolute value of 3x minus 9 is greater than or equal to 9. So again, what I really like to do is I see that greater than or equal to symbol, and a lot of students really struggle with understanding why your solutions look like this, which I explained in the beginning. That is really difficult to understand. So if you're still confused on why that is, just understand that many students feel that way. It's pretty difficult. So this is an OR. That's going to be your solution. It's going to be an OR compound inequality. So now let's set up our cases. We've isolated our absolute value expression, and in case 1, which I'll just do this, in case 1, we're going to drop our absolute value bars, and we're going to solve that. In case 2, and we're going to have an OR there. In case 2, I'm going to drop my absolute value bars, but then what do I do to my sign? I flip it, and it's not +9, it becomes -9. And now let's solve for your simple inequalities that will result in your compound inequality. So in case number 1, if I add 9 to both sides, I get 3x is greater than or equal to 18. And when I divide both sides by 3, I get x is greater than or equal to 6. There's one of my simple inequalities for my solution. In the next case, if I add 9 to both sides, I get 3x is less than or equal to 0. And then if I divide both sides by 3, I get x is less than or equal to 0. So this is an OR compound inequality. I have x is greater than or equal to 6. So I'm going to have a closed dot at 6, and it's greater than. And then x is less than or equal to 0. Closed dot at 0, less than. So there's my OR inequality. And how could I write this? You can absolutely just write it like this as your answer. If I wrote it in interval notation, what would it look like? Let's change colors again because just why not? From negative infinity to 0, parentheses or brackets? Brackets, or brackets 6 to infinity. You can absolutely write it like that. Let's move on to number 3. So number 3, the absolute value expression is already isolated, so I don't need to do anything to get it isolated. It's already like that. This is a less than or equal to problem, which means my solution is going to be and. So the absolute value of all of this needs to be less than or equal to negative 10. So let's just set up our cases. So the first case, I'm going to drop my absolute value bars. 8x minus 6 is less than or equal to negative 10. And in the second case, I'm going to drop my absolute value bars, flip my sign, switch the number, positive 10. And now let's solve. So in this first case, when I add 6 to both sides, I get 8x is less than or equal to negative 4. And then when I divide both sides by 8, I get x is less than or equal to negative 1/2. And in my second case, if I add 6 to both sides, I get 8x is greater than or equal to 16. When I divide both sides by 8, I get x is greater than or equal to 2. So now if I were to graph this, let's see, x is less than or equal to negative 1/2. Okay, less than or equal to, if I were to just do this, it would look like that. And x is greater than or equal to 2. Now I really like to solve this all the way through. This is an and compound inequality. A lot of students, when they see this, will think, oh, and they'll just go about solving it and there's your answer and we're done. This is an and inequality. Your and compound inequalities are where your simple inequalities overlap. We don't see any of that. The absolute value answer is greater than your negative number. Therefore, there is no solution. So if you ever see, and I'm going to write this right here, if you see an and compound inequality and your solutions look like this, there's no solution. If you see an or compound inequality and your solution looks like this, your answer is all real numbers. So you can have those special cases, right, where you got to think about your and inequalities and your or compound inequalities. So let's move into our very last example. Problem number 4, the absolute value of 2x divided by 3 plus 3 is greater than 7/3. So it's greater than, which means it's an or compound inequality. So when I'm dealing with fractions, especially if I have the same denominator on two of them, it's just automatically, I want to get rid of those denominators. I don't want to deal with fractions. So what can I do? I can multiply everything by 3. When I multiply everything by 3, we keep our inequality proportional, if you will. So when I multiply, I'm going to distribute this into basically every term across the inequality. So when I multiply 2x over 3 by 3, I get 2x. When I multiply 3 times 3, I get plus 9. There's my absolute value is greater than. And when I multiply 7/3 by 3, I get 7. And so now I've created an absolute value inequality where I don't have any denominators to deal with. And so I can actually just set this up like we did on all of the other examples. This is an OR compound inequality. Because it's absolute value, I need to set up two cases. In my first case, I'm going to drop the absolute value bars. 2x plus 9 is greater than 7. In the second case, I'm going to drop the absolute value bars, flip the sign, switch the number, -7. And now we're just going to solve. This is an OR compound inequality. That's going to be my answer. So in this first one, when I subtract both sides by -9, I'm going to get 2x is greater than -2. When I divide both sides by 2, I get x is greater than -1. There's one part of my solution. In the second case, when I subtract both sides by -9, I get 2x is less than -16. And when I divide both sides by 2, I get x is less than -8. So my solution is x is greater than -1, or x could be less than -8. So what does that look like? Well, x is less than -8 looks like that. What about x is greater than -1? Well, here's -1 greater than -1 would look like that. So you can absolutely write your answer like this. You could also write it in interval notation. So from -infinity to -8, parentheses or brackets, parentheses, we have an open dot. We are excluding the point -8, or -1 to infinity. And that concludes your notes over solving absolute value inequalities. This typically can be a frustrating topic for a lot of students, so if you're struggling with it, you're just like most students, but I hope this was helpful.